Okay, let's move on to question 6. So question 6 is also a diffusion equation question, right? So question 6 looks like this. Okay, and again, I've summarized the question for you, right? So essentially, two parts, 6a and 6b. Right, both are diffusion equations. For 6a, your boundary conditions are such that at x equals to 0, big T is 0, and x equals to 2, big T is also 0 at all times. For part A, the initial condition is given as 100 sine pi x. Now part B is the same diffusion equation except that the boundary conditions are slightly different. The first boundary condition is the same. Second boundary condition, instead of being at 0, is now 100, and you also have a slightly different initial condition. Okay, let's start solving the question. Let's do 6a first. Alright. Okay, and since it's a diffusion equation, okay, all I've done so far is just to copy the general solution from the formula sheet for the diffusion equation, and I'll call this equation 1. Okay, so as with other problems, I will start with the boundary condition. So I'm going to put boundary condition 1, which tells me that big T is 0 at x equals to 0. Put it into the solution 1, and then that just gives me, so I'm just putting x equals to 0 here, here, and here, so we get C. Okay, dx becomes 0 plus a cos 0 is just a, alright, plus b sine 0, so this term is also 0, so we just get this. Okay, so I've cut back some steps because I think you should be familiar with it by now. So this must be equal to 0. Okay, and from this you can then tell that C must be 0 and A must be 0. Okay, so you put C equals to 0 and A equals 0 back into equation 1. And then you can see that your updated solution becomes, okay, so C is 0 and your A is also 0, right? So these two terms go away, so you're just left with dx plus b sine omega x times e to power minus k omega squared t. So that's my updated solution, equation 2. Alright. Okay, now I'm ready to put in the second boundary condition. Okay, so I've already used the first boundary condition. Okay, and I'm ready to use the second boundary condition. Alright, so I'm going to put the second boundary condition, which tells me that big T at x equals to 2 is equal to 0. Okay, so I put that into my updated solution, which is equation 2. And what I get now is I just put x equals to 2 here and here. You get 2d plus b sine 2 omega times e to power minus k omega squared t. Now this has to be equals to 0, right? Equals to 0. Okay, so again you have to ask yourself the question, this has to be equals to 0 at all times, at all values of t. Okay, so what that means is you need d to be 0 Okay. Again, we don't put b equals to 0, right? Because if you put b equals to 0, you have nothing left in your solution here. Okay, so we make sine 2 omega to be 0. Alright, and that means that the angle 2 in omega must be a multiple of pi. Okay. Alright, so that tells you have multiple values of omega. Okay, so I'm going to put this information d equals to 0 and omega equals to r pi over 2 into equation 2, okay, the updated solution. So now I can say that equation 2, the updated solution, becomes, okay, so d here is now 0, so there's no d, okay, plus, sorry, okay, that d is 0, so this is b, alright, so this is, just to remind you, this is 0, sine, omega here is now r pi over 2, so you have r pi over 2x e to the power minus k, omega squared t is again r pi over 2 squared t, alright, and remember your r takes on the value of 1, 2, 3 and so on, right? So as with all the other questions, we want all the solutions, okay, all the solutions corresponding to r equals to 1, 2, 3 and so forth. So we sum them up, okay, and label the b as br, because every solution has its own coefficient, right? So we don't need this statement anymore. It's all written into here. Okay, so this now becomes the latest updated solution, which I call equation 3. So how do we determine the BR here? Okay, we make use of the initial condition. Okay, alright. Okay, so what I'm going to do is I'm going to put the initial condition which tells me that at small t equals to 0, big T must be equals to 100 sine pi x. Okay, I put this into my updated solution, equation 3. Alright, so and that will give me, so all I'm doing now is to put t equals to 0, right? So t goes here. So I'll get summation of BR sine r pi x over 2 times e. Okay, so t becomes 0 here, so it's e to the power 0. Right? So this must be equals to 100 sine pi x. 100 sine pi x. Okay, so e equals to 0 is just simply equals to 1. Right? Let me use red. This is just equals to 1. Right? Okay, so if it's equals to 1, then basically you can just see that this is just a sine series expansion of the function sine pi x. Okay, So again, at this stage, you can now find BR. Okay, alright. You can find BR. You can say that right, this is a sine series expansion of fx equals to 100 sine pi x, right? So this is like my fx. Okay, this term here. Right? So from there, you can then tell that the coefficients of the sine series, okay, is just the 2 over L integral from 0 to L, okay, fx times sine r pi x over L dx, okay, where L is 2, right? L is 2. Okay, you can see the 2 is coming from here. Okay, right, and 2 is also the length of the rod. Okay. And fx is simply 100 sine pi x. Okay, so you put L equals to 2 here, and you put 100 sine pi x into here, you do the integration, you can find the BR. Alright. Now of course, if you are, well, if I wouldn't say of course, but if you are sharp enough, you can also do like what we have done before. You start expanding out this term. Okay, you start expanding out this term. Okay, so this is for I equals 1 to infinity, so you get b1 sine, so I equals to 1 is pi x over 2 plus b2 sine, okay, when r is 2 you get 2 over 2, so we're just left with pi x. Plus b3 sine, okay, 3 pi x over 2 plus and so on. Okay, so this will be your left hand side of this equation. So this must be equal to the right hand side, which is 100 sine pi x. Okay, right? Okay, you cannot always do this, right? Sometimes you have no choice, you have to do the Fourier series integral to get your BR. But in this case, it just so happens that the right hand side is equal to one of the terms on the left hand side when you do the expansion. Right? This is basically a design question to make it easier for you. So this term you can see matches this term. Right? So therefore you can tell that your B2 must be 100, and all your other B, your B1, your B3, B4, B5, and so on, they are all 0. Okay? So you put this information for all your coefficients B back into your solution. Okay, remember which is your solution? Your solution is equation 3. Okay, your solution is equation 3. So you put all these coefficients back into 3. Okay, therefore your solution, which is equation 3, then becomes, okay, right, so you have many BR terms inside here, but only one is not 0, the one that corresponds to R equals to 2. Right, so R equals to 2, when R is equals to 2, B2 is 100 sine r equals to 2 here, this becomes 2 over 2, so it's just pi x times e to the power minus k. Again, r is 2, so 2 over 2, so you just left with pi here, pi squared t. So this is your answer to question 6a. Alright, so this is the answer to question 6a. Okay. Now, let's do question 6b. Let's do question 6b. Okay. Now, if you take a look at question 6b, you will realize that the first boundary condition is the same, right, as question 6a. Alright, which means that, okay, when I start the question, things look the same, right? I start with the general diffusion equation solution. Okay, the first boundary condition for 6a, okay, so this is question 6a, it's the same as 6b, alright? So when you put in the first boundary condition, which is the same for 6a and 6b, you'll find that you will still end up with this. Okay, you'll still end up with this. Okay, right? So for question 6b, okay, after you put in the boundary condition 1, you still have the same equation 2. Alright? Alright. Okay, so I'm doing 6b now. Okay. So I'm doing question 6b now. Okay, and the equation is, so after I've used, as explained, after I use the first boundary condition, which is the same as 6a, I will get this. Okay, so after BC1, I will get this. Okay. Okay, so also let me call this 2, okay? Right. Okay, so now next thing to do is I'm going to put in boundary condition 2. Okay, so this condition is different from the second boundary condition of 6a. So I'm going to put in boundary condition 2, which tells me at x equals to 2, big T is 100. Okay, and what's that give me? Okay, I put x equals to 100 here. So and here, so I have 100d plus b sine 100 omega e to the power minus k omega squared t. Okay, now this must be equals to 100, right? Here. Okay, and this must be equals to 100 for all values of t. Alright, so how do I make the left hand side equals to 100 for all values of t? Oops, sorry, mistake. Okay, I should put x equals to 2, right? X equals to 2, not x equals to 100 here. So sorry, let me redo this statement. Okay, so I put x equals to 2, so this is 2d, right? X equals to 2 here, not 100, plus b sine 2 omega e to the power minus k omega squared t this must be equals to 100. Okay, so for all values of t. Okay, so how do I get the left hand side to be equals to 100 regardless of the value of t here? Alright, so you can see that this means that my 2d must be the one that gives me the 100. Okay, right, and at the same time this term must be 0, right? Because this already gives me the 100, so this term must be 0, right? So how do I make this term always 0, even though t can be changing for any value, right? Well, you could make b equals 0, but if you make b equals 0, right, you just throw away this whole term of your solution. Okay. So again, a less or a more flexible way of making this term always 0, okay, is to get sine 2 omega equals to 0. Okay, right. So this means that for this case, this 50, and this means that for this case, the 2 omega is equals to r pi, which means that your omega is r pi over 2, where r can take on any positive numerical value, or integer value, positive integer value. Okay, so I'm just going to make use of this information, d equals to 50, and omega equals to r pi over 2, and put it back into your solution, which is equation 2. So this is 50, omega here and omega here are r pi over 2. Okay, so therefore I can update my solution. Alright, so d is 50 plus b sine omega is r pi over 2, r pi over 2 times x, e to the power minus k, omega again is r pi over 2 squared t. Okay. Alright, so again, your r takes on the value of 1, 2, 3, and so on. So what we want to do is we want to sum up all the solutions for the different r values, just like before. Okay. So this is then my updated solution, which I call 3. Alright, so how do we find the BR? Well, same thing, you go look for the initial condition. This one. Okay. So I'm going to put the initial condition into my updated solution. Okay. So this is my initial condition. Okay, I'm going to put it into updated solution, which is equation 3. And then what you get is, so I'm going to just put t equals to 0, so I get 50x plus, so you put t equals to 0 here, br sine r pi x over 2 e to the power of 0, right? And this must be equals to 100 sine pi x over 4. Okay, so what I'm going to do now is I'm going to put e to the power 0 as 1, and I'm going to bring this 50x over to the right hand side. Okay, so I have now Okay, this is equals to 100 sine pi x over 4, bring the 50x over, minus 50x. Okay, so I'm going to call this fx. Okay, so you can now see this is sine series expansion of fx. Okay, which means you can now use the sine series formula to find BR, which is given by 2 over L, this is 2 over L, integrate 0 to L, fx sine r pi x over 2 dx. Okay, so in this case you can see that your L here again is 2. Okay, and your fx here is this expression here. Alright, and there you go. Okay, so I'm not going to do this integration for you. Okay, so I just give you the statement for finding BR. So this is 2 over 2, 0 to 2. Fx is 100 sine pi x over 4 minus 50x. Okay, this is your fx. Okay, and you need to multiply this by sine r pi x over 2 dx. Okay, and then you go through the working and you find that your BR, okay, I'm just going to write down the answer for you. Okay, you find that your BR, okay, so you do all the working, you find BR is 800 times R times minus 1 to the power of R plus 1 over 4R squared minus 1 pi plus 200 over R pi, okay, times minus 1 to the power of R. Okay, right, so this expression for BR, goes back into equation 3. Okay, and that will give you the final answer. Okay, so I'll just make a remark here. Put this expression for BR into equation 3, which is your updated solution, to get final answer.